Today I will be presenting the paper Effective Seed Scheduling for Fuzzing with Graph Centrality Analysis, published at IEEE Security and Privacy in 2022. This paper addresses a fundamental challenge in modern software security testing. When a fuzzer runs for a long period of time, it accumulates thousands or even millions of candidates' inputs that could be tested further. However, the fuzzer cannot explore all of them equally due to limited computational resources. The central question becomes how to intelligently decide which input should be tested next. While many people assume fuzzing improves simply by running faster or producing more mutations, the authors argue that smarter decision making is actually the key to effective exploration. Their contribution introduces a scheduling strategy inspired by graph theory, allowing fuzzers to prioritize inputs that are structurally positioned to uncover new execution paths and previously undiscovered vulnerabilities. To understand the motivation behind this work, it helps to imagine exploring a massive maze while searching for hidden treasure. At every intersection, there are multiple possible paths, but only some lead into unexplored territory. If explorers choose directions randomly, they frequently revisit areas that have already been mapped, slowing overall progress despite continued movement. The real challenge is not how fast explorers move, but how intelligently they choose directions. Fuzzers behave in a very similar way when testing software. Each input sent into a program causes execution to follow a particular path through the code. Some inputs explore completely new logic, while others repeat previously observed behavior. Efficient fuzzing depends on directing exploitation outward toward unknown regions rather than repeatedly revisiting familiar ones. Fuzzing is an automated software testing technique in which programs are executed repeatedly using automatically generated inputs. A fuzzer continuously produces new inputs, runs the program, and monitors execution for crashes, hangs, memory violations, or unexpected behavior that may signal security vulnerabilities. Modern software systems accept extremely complex inputs, making manual testing impractical. Fuzzing solves this challenge by exploring the input space automatically at extremely high speed, often performing millions of executions per hour. Because of this scale, fuzzing has become one of the most successful vulnerability discovery techniques used in industry today. Major organizations such as Google, Microsoft, and Apple rely heavily on fuzzing to detect software flaws before they can be exploited by attackers. Most modern fuzzers use a technique called gray box fuzzing, which was popularized by the AFL fuzzer. The process begins with a set of seed inputs that successfully execute the program. These seeds are mutated slightly to produce new candidate inputs. Each mutated input is executed and the fuzzer measures code coverage, which indicates which parts of the program were reached during execution. If an input causes the program to execute previously unseen code, that input is considered interesting and saved for future mutations. This creates a feedback loop where successful discoveries guide future exploration. Over time, the fuzzer gradually expands coverage across the program, exploring deeper and more complex execution paths. Do you see the process of how a fuzzer comes to the conclusion when it comes to finding vulnerabilities? As fuzzing continues, the number of saved seeds grows rapidly, A long-running fuzzing campaign may accumulate thousands or even millions of inputs. However, computational resources such as CPU time are limited, meaning the fuzzer cannot spend equal effort mutating every seed. This creates a critical scheduling problem, determining which input deserves additional testing because they are more likely to lead to new discoveries. If the scheduler chooses poorly, the fuzzer wastes time repeating known behaviors. If it chooses well, exploration accelerates dramatically. Seed scheduling therefore becomes one of the most important factors influencing fuzzing effectiveness. Do you see how comparing it to a maze can often help you get a better visualization about how a fuzzer chooses which path it takes? Traditional fuzzers rely on relativity, simple heuristics, to choose seeds. Some select inputs randomly, while others prioritize inputs that execute quickly or have smaller sizes. Although these strategies are computationally inexpensive and easy to implement, they lack awareness of relationships between inputs. Two seeds may look different syntactically, but execute nearly identical code paths internally. Because traditional schedulers treat them independently, fuzzers often spend excessive time exploring redundant behaviors. This limitation prevents efficient expansion into unexplored region of the program. If the fuzzer gets caught up in a loop, it will not advance until it gets through this loop. This inefficiency can again be understood using the maze analogy. Imagine many explorers entering a maze, but remaining clustered near the entrance, repeatedly mapping the same nearby corridors. Even though exploration is happening continuously, progress slows because effort overlaps heavily. Fuzzers behave similarly when they repeatedly mutate seeds that trigger nearly identical execution paths. The author argues that current fuzzers lack a global understanding of how exploration is distributed across the program, which prevents them from directing effort toward areas with the highest potential for discovery. The key insight introduced by this paper is to treat fuzzing inputs not as isolated test cases, but as interconnected elements of a graph. Each seed becomes a node, and relationships between execution behaviors create edges connecting nodes. As you can see in this image, all the nodes are connected by edges. By constructing this graph, the scheduler gains a structural overview of how inputs relate to one another. Instead of guessing which seed might be useful, the system can analyze the structure of exploration itself. This transforms seed scheduling from a heuristic process into a problem that can be solved using established graph analysis techniques. A helpful way to understand this idea is through social networks. In a network of people, some individuals connect multiple communities, just like LinkedIn, Facebook, and Instagram, while others remain isolated at the edges. These would be apps that are more specific to what the user wants. Graph theory provides mathematical tools that measure how influential or strategically positioned each individual is within the network. The authors apply this same reasoning to fuzzing seeds. Each input occupies a position within a network of execution behaviors, and that position reveals how valuable the input may be for further exploration. Centrality is a measure used in graph theory to determine how important a node is within a network structure. Some nodes act as hubs, connecting many others, while bridge nodes connect otherwise separate clusters. In fuzzing, bridge-like seeds are especially valuable because they may lead into unexplored regions of program execution. By identifying seeds with high structural importance, the scheduler prioritizes inputs that are more likely to expand coverage rather than repeat known behaviors. This replaces random guessing with informed decision-making based on network structure. After centrality scores are computed, the scheduler assigns higher priority to seeds occupying strategically important positions in the graph. This encourages exploration to spread evenly across the execution space rather than clustering in a small region. Instead of relying on local heuristics, the fuzzer now uses global structural information about all discovered inputs. This allows exploration decisions to consider the overall shape of the search space, leading to more efficient discovery of new paths. The workflow begins by collecting execution coverage information during fuzzing. Using this data, the system constructs a graph describing relationships among seeds. Centrality metrics are computed to evaluate each node's importance within this structure. These scores determine which seed received more mutation attempts. Importantly, the mutation engine itself does not change. The improvement comes entirely from better scheduling decisions, which makes the approach practical and easy to integrate into existing fuzzing systems. The authors evaluated their scheduling strategy by comparing it directly against standard AFL scheduling methods across multiple benchmark programs commonly used in fuzzing research. These programs varied in size and complexity, allowing the researchers to test whether their approach worked consistently rather than only in narrow situations. The primary measurement they focused on was code coverage over time. Since increased coverage strongly correlates with discovering new program behaviors and potential vulnerabilities, their results showed that the graph centrality scheduler reached higher coverage faster than traditional approaches. In many cases, the improvement appeared early in execution, meaning the fuzzer began exploring useful regions sooner rather than wasting time in repeating already known paths. Additionally, the system discovered more unique crashes, suggesting that improved exploration directly translated into improved vulnerability discovery. One important takeaway from these results is that no changes were made to mutation strategies or input generations. The improvement came purely from making smarter decisions about where to spend computational effort. The effectiveness of this approach comes from its ability to capture global structural relationship between inputs. Traditional heuristics make decisions using local information such as execution speed or input size, which provides only a limited understanding of exploration progress. In contrast, graph centrality considers how each state relates to all other discovered seeds. Inputs that lie near unexplored regions naturally receive higher importance because they serve as gateways into new execution paths. This means the scheduler implicitly predicts exploration potential without explicitly analyzing program logic. By continuously prioritizing structurally important seeds, the fuzzer avoids repeatedly testing redundant behaviors, saving time on finding vulnerabilities. Over time, this causes exploration to expand outward in a balanced way, similar to a wave spreading across the program's execution space. The key insight is that understanding relationships between inputs is more valuable than evaluating inputs individually. By understanding the relationships, you cut down the time that the program would run, because finding similarities between them would help find vulnerabilities faster. One of the strongest aspects of this work is how practical the proposed improvement is. Rather than redesigning fuzzing entirely, the authors focus on a single component, scheduling, and improve it using well-established graph theory concepts. Because mutation strategies remain unchanged, existing fuzzers can adopt this method without major architectural modifications. Another strength is conceptual clarity. Graph centrality has been studied extensively in many domains, including social networks and transportation systems, meaning the theoretical foundation is well understood. The approach is also flexible and generalizable, since it does not depend on specific input formats or particular program types. This makes the technique broadly applicable across different fuzzing environments. Overall, the paper demonstrates that meaningful performance gains can come from smarter organization of existing information rather than increasing computational power. Despite its advantage, the approach introduces several trade-offs. Constructing and maintaining a graph of relationships between thousands of seeds requires additional computation and memory overhead. As fuzzing campaigns grow larger, updating centrality metrics may become increasingly expensive, potentially offsetting some performance gains. Another limitation is reliance on coverage accuracy. If instrumentation fails to capture meaningful execution differences, the resulting graph structure may not accurately reflect exploration progress. In such cases, centrality scores could prioritize suboptimal seeds. Additionally, graph construction introduces complexity into what was previously a lightweight scheduling process, which may make implementations more challenging in extremely resource-constrained environments. These limitations highlight an important theme in system research. Improving intelligence often introduces additional computational costs. This work opens several promising directions for future research. One possibility is combining graph-based scheduling with machine learning techniques that dynamically adapt prioritization strategies over time. Instead of computing static centrality measures, a learning-based system could observe which scheduling decision historically produced new coverage and adjust behavior accordingly. Another direction involves hybrid scheduling approaches that combine structural graph information with semantic program analysis, potentially improving prediction of unexplored execution paths. Researchers may also explore incremental or approximate graph algorithms to reduce overhead while preserving benefits. More broadly, this paper suggests a shift toward viewing fuzzing as an intelligent search process rather than a purely random mutation engine, encouraging future designs that integrate insight from data science and network analysis. The central lesson of this paper is that fuzzing effectiveness depends not only on generating large numbers of inputs, but on allocating effort intelligently. Traditional fuzzers treat inputs largely independently, but this work demonstrates that relationships between inputs contain valuable information about exploration progress. By modeling fuzzing as a network and applying graph centrality analysis, the scheduler gains a global understanding of the search space. This allows exploration to become more strategic, reducing redundancy and accelerating discovery. More broadly, the paper highlights an important principle in computer security and systems design. Smarter organization of information can produce significant improvements even without increasing computational resources. In conclusion, this paper presents a novel perspective on fuzzing by transforming seed scheduling into a graph analysis problem. By applying centrality metrics, the authors enable fuzzers to identify structurally important inputs that are more likely to lead toward unexplored program behavior. Experimental results demonstrate improved coverage growth and increased bug discovery, showing that intelligent scheduling alone can significantly enhance performance. Beyond the specific technique introduced, the work illustrates how ideas from other scientific fields, such as graph theory, can meaningfully advance software security testing. As software systems continue to grow in complexity, approaches that guide automated exploration intelligently will become increasingly important. This paper represents an important step toward more strategic and efficient vulnerability discovery.